When we first talked about double integrals, the first thing we talked about was how it related to geometry and how we say a double integral, kind of like its equivalent single integral back in Calc 2. A single integral is finding the area under the curve. A double integral would be finding a volume under a surface. So a triple integral would take that a step further, which now is difficult to visualize as a geometry problem. It still can be a geometry problem, and we will look at that eventually. But for now, we can begin the discussion of a triple integral with one of the applications that we already kind of figured out, which is like a density or something. So let's start off with an application, and then later on we'll get into the raw geometry of it. And there's going to be some cool problems coming up. And so the natural thing to do is to go over the mass density problem. So what we could do is we can imagine that we have, we're looking for the density of the solid. So I think the first time I talked about density in the double integral application was I wrote down like 3 formulas for density, or for mass. Mass equals density times the length, mass equals density times the area, and mass equals density times the volume. And with the double integrals last time we talked about, we're essentially talking about density times the area. And then we're looking at the area of a lamina, a plate that's 2-dimensional, and how it would change density as you move along the different parts of the plate. Well, we can also now talk about the density as a measurement of how dense a particular volume is. And we can say that a density function can be a function, was it rho or delta? You guys didn't like delta rho. As a function of density of a particular solid is dependent on where you are in that solid. Now I'm saying solid now because I have to talk about volumes. This is some 3-dimensional solid, and not just surfaces on the outside, but surface that's actually filled in inside as well. So our density function can be given as rho as a function of x, y, and z, and this would be grams or kilograms or whatever per volume per cubic meter or something as an example. This is a g. So what we need is, I can't draw my fancy surface anymore because that's just z is equal to f of x, y, but we could think about a solid, and anyways, I probably shouldn't be drawing the surface anyways. So let's give it some curves to make it look 3-dimensional. So this is a solid, and at each point of the solid has a certain density that may change as you move around from different points of that solid. And this would be your region, and our region we called R, or maybe they called it D. So for this one, the notation, I don't know what the book uses. I think they use E. I had an old book that used capital omega, which is kind of cool, because then you write that a bunch of times, and it's cool to write, right? I mean, doesn't it look like a cool letter? All right, we'll use E. So the mass for this case then is going to be a triple integral now over solid, that solid of your function. Now, so now we need to take a look at an area element. And an area element can be seen as within this region, inside of this solid region, we can think about having a small block, a box, that would have delta y, a delta x, and a delta z, some small change in x, y, and z, where that can be combined together as a volume element. That would be dV. So without going through the Riemann sum story, well, a quick Riemann sum story synopsis is for each of these little blocks, I would find a representative point from that block to be the density function at that block, and then I would take this volume of this block and multiply it by the density to get the mass. So I would get the small mass of this little block, and then I would add up a whole bunch of blocks as my x, y, and z changes. And so my delta V will become a dV now. So this is an example of a triple integral where it would be useful to be able to calculate triple integrals. A physical example. Okay? So you don't have to ask, what's that good for? All right. We can extend this to the other applications that we've been talking about, like probability. Now, instead of having a 2-variable probability problem, we can have a 3-variable probability problem. We can find the center of mass the same way. This one, it's harder to think about, balancing this on a particular pin, but we can think about maybe drilling an imaginary hole and then holding this object, this solid, by that point somewhere in the middle to balance out and make sure it doesn't move one way or the other. It's that would be the center of mass. And then the average value business, so all those applications that we've had before can also work here. All right. Is this motivation enough to be able to talk about triple integrals? Okay. All right, too bad. That's all you get. Let's do an example. Oh, I forgot. I can't do that. So the important parts about doing a triple integral, as you probably saw in the double integrals, is focusing on the region that you're integrating over. In this case, it's a solid that you're integrating over. All right, so if we pick one like number 13, for example, where we're asked to evaluate this double integral. So it's a double integral of 6xy, so we can pretend that 6xy is your density function. And then you have a solid. A solid E is going to be a solid where it's bounded above by a plane. Oh, it's going to be hard to draw this, huh? Well, it's bounded above by a plane and below by the region on the xy plane that looks like this. Y is equal to square root of x. I think it goes like that. Y is equal to 0. Y is equal to 0 is the x-axis. And x is equal to 1. And then somewhere in 3 dimensions, there's this plane and this is your two-dimensional region that would get projected up to the plane somehow. And so we're looking at that volume right here. Okay. Damn, that's a good drawing.
It is. I was really impressed.
Oh, did I do it backwards? La la la. Wasn't such a good drawing after all, huh? That one's not so good anymore. All right. So I want to try to stress the idea that you don't have to be a good drawer to be able to do this. You don't have to be able to visualize this in all its details in 3 dimensions, although it would be nice if you can. But if you can't do it, the hard part is trying to see what the first integral is going to be, and then once that's done, you squash it down to 2 dimensions. Okay? So what I'm trying to say there is that if you look at the problem, and if you look at some keywords like E lies under the plane, so I know that plane is going to be the top function. And I'll call it z function because I might be interested in integrating with respect to z first. And then above the region in the xy plane, and so now the xy plane kind of gives me the hint that that's probably my bottom function. And the xy plane is z is equal to 0. So when I want to set up my triple integral is going to be set up the way I have my x, y, and z down below, except I would write it z since I want to integrate with respect to z first. I would write my inequalities like this. And then once you figure out your z limits, you're down to x and y. And what that means is that you can forget about your 3-dimensional picture and look at what happens in your x and y, and then treat it like a double integral. So you still have to be able to draw in 2 dimensions and draw all those functions that you've gotten to know since pre-calculus. And be able to run through the same double integral process that we've had. So the hardest part, I think, is trying to, in terms of visualizing this, trying to see what happens in the 3rd dimension. And I always say 3rd dimension because I don't just want to say z, integrate with respect to z first, because there's going to be some times where you might be interested in integrating with respect to x first as well, as in one of your problems is going to ask you to do. So if you can do this in 3 dimensions, you're looking at z values. We already have our z limits, right? But if you're drawing this in 3 dimensions, you would go through the same process that you did before. I'm integrating with respect to z first. I will draw a line parallel to the z-axis and ask myself when I'm going to enter my region, my 3-dimensional region. I would enter my 3-dimensional region when z is equal to 0. And I'll be inside of the region until I exit my region. And I will exit my 3-dimensional region when I'm at that plane. Z is equal to 1 plus x plus y. So those are going to be my limits for my z, and that's going to be my innermost integral. So the first limit that you get is going to be the innermost integral. After that, I got a 2-dimensional problem, and looking at this region now, two-dimensional region, I can integrate with respect to whatever I want. What do you want to integrate with respect to? With respect to y. First. With respect to y first, draw a line parallel to the y-axis. I will enter my region y is equal to 0, and I will exit my region y is equal to the square root of x. Outer limits are always, always, always constants, 0 to 1. I'm done, kind of. Yeah. I don't think there's symmetry for this problem. The plane is tilted. That's going to change things. And this is like a parabola, but it's only half of a parabola. So I don't know if there's much symmetry going on here. Oh, in general, if you see something that's circular, if this was a whole parabola and in the plane, well, the plane has to be the plane, or maybe the shape dips up and goes back like a parabolic shape. So I think circles and parabolas that are equal on both sides, but you'll have to be able to see the third dimension and agree that there's going to be symmetry there too. So I think taking advantage of symmetry would be a little trickier. And usually when we see something that's circle-like, instead of taking advantage of symmetry in x and y, we probably just want to go polar for that. Right?
So when you were doing double integrals, if you do x or y first and x on the other, it's a z, right?
Yeah.
When we find the limits at z, does it affect the limits of x and y?
No, because whatever we get for the first integral, the inner integral, whatever we get for the inner integral, we're just going to squash it down to the other two variables.
But then you still have to do either x or y first.
Yeah, yeah. All right, so let's just write out the integral. This is going to be a triple integral now. The innermost integral, well, first let's write down our function. This is our integrand, 6xy. And instead of dv, now that we have the limits, we can break it up to dx, dy, dz in whatever order we need to. So we agreed to take the derivative or the integral with respect to z first, and our z limits go from 0 to 1 plus x plus y. And then we're going to go with respect to y from 0 to square root of x. And then we're going to go with respect to x from 0 to 1. And as you see, there are x's and y's in the limits, so we're not going to be able to break this apart into separate integrals like we've done. Okay, you can only do that if you have constant limits. So constant limits are really, really helpful in making our calculations really easy, but in this case, it's not like that. So I know if I ask, should I do this integral, you'll say yes. So I'm not going to ask.
So the question that I asked you yesterday, I could do what I want, since I could take out 6x.
Well, no, you can't for this one because there's an x and a y here.
There's no z.
Oh, yeah, there's no z. That's right. All right, let's do it. So, yeah, so.
It makes it easier for me.
Yeah. Oh, it's true. So what Bianca is saying is that there's a z here. I'm integrating with respect to z, and there are no z's here. So this is constant. So let's do this integral. Inside integral here, I could take the 6xy out, and then I would integrate 1 dz from 0 to 1 plus x plus y. That says x plus y there. Equals 6xy is your constant, and then your integral is just z, and then you put in 0 and 1 plus x plus y. And so you get 6xy times 1 plus x plus y minus 0. So that's the first integral, the innermost integral. And we can even simplify that, I suppose, to make it in pieces instead of a product. 6xy, 6x squared y, and 6xy squared. Okay, now let's integrate that with respect to y. The next integral from 0 to square root of x. This is our new integrand, 6xy plus 6x squared y plus 6y squared, xy squared, dy. And now you can break this up to 3 integrals and or factor out anything with an x in it and then move it outside. I don't know, that seems like it's too much work. I'm just going to keep it like this. And remember that this is with respect to y. So the integral of 6xy squared with respect to y would be y squared over 2, right? So the 2 and the 6 would cancel, so that'll give me 3xy squared. And another y squared over 2, so 3x squared y squared. And then now this is y cubed over 3. So 2xy cubed, and then the 3 would cancel with a 6. And I have to remember that these are my y values that I'm going to replace from 0 to square root of x. So if I put 0 in there, it's all going to be 0, so I just put square root of x in for y. And for the first one, I'm going to get 3x squared, square root of y, square root of x, quantity squared is just x. The same thing, 3x cubed this time. And then now this is not so nice. I would have 2x times x to the 3/2 power. So I would add the powers, right? 5/2. Yeah? I don't think so, because this is y cubed, and in for y, I'm going to replace it with an x squared, or I'm sorry, a square root of x. So square root of x is x to the 1/2 power, right? And then you multiply 3 times 1/2, so that's 3/2. Is that right? Okay. And then this is just 1, so that makes it 5/2. Whew. All right, now we have a function in x that we can integrate with respect to x. And so finally, our integral from 0 to 1 of 3x squared plus 3x cubed plus 2x to the 5/2. This time with respect to x. No. X cubed, 3/4, x to the 4th, and add 1, so that's 7. 2 over 7, so that's 4 over 7, x to the 7/2. And then you put 1 in and you're done. Okay. This is not a volume. This is, if this is a density of that solid, of this shape, then this is the mass of that solid, not the volume. Good point. So say not volume. And then we can say on the side here, if 6xy is the density function, then we just found the mass of the solid. Yes, but we'll do that in a minute. Okay. Yeah, yeah. I hope so. Right. Yes. So I hope so. Unless they do something weird. I think they did this in one of the homework problems where they say that the density is proportional to the distance from the origin. In that case, you have to come up with your density function. But I'm not planning to do anything like that. But if there's homework, it's homework. All right. More questions? Okay. Jesus, can you ask your question again? Isn't the volume of the density function is 1? And I said yes. So I want to go back to a double integral. If we have a double integral over some region D, and then we have 1 dA, what we're saying is that the height of that plane, or the height of that z is equal to f of xy function is just 1. And then I said numerically that this is just the area of whatever the domain is, right? And this is silly to think of, but we can even go backwards. If we integrate from a to b of 1 dx, then this is equal to b minus a, which is the length of the interval a to b. So think about that. This is a one-dimensional length measurement, and the integral over that interval, if you have 1 in the integrand, the integral of that interval is just going to be the length. For a double integral, this is some d region in a domain in your xy plane, and if your integral is 1, and if your integrand is 1, that's the area of D. So it seems natural to think about a triple integral and if your integrand is just 1, then this must be the volume of your solid, whatever that solid is that you're talking about. Think about it as a density function of 1. At each point, it's constant. Yeah.
So basically, to make triple integral for volume, would that be useful when you don't have like a height function?
Probably. But you know, a triple integral, maybe your volume is in a way where it's easier to integrate with respect to x2 first. And so you might want to integrate with respect to x first. And in which case, you know, you can see it as a volume. Or we'll see what happens here. It'll be exactly the same thing. We'll do an example where we're looking for the volume of something. We can look at it as a double integral or a triple integral. Well, first we'll look at it as a triple integral, and then we'll see that it becomes a double integral.
In 2D, what's the equivalent of the density that we have?
Well, it's like the plates that we were looking at the other time. It's what? You're probably right. So it's like the lamina, the plates. We have a plate, and then it has a different density at each point on the plate. And so we would find the mass by doing a double integral. Yeah? Yeah. That's always going to equal to 1, whether you're in 1 dimension, 2, or 3 dimension. All right. Let's see if we can find a volume problem. So use triple integrals to find a volume of a solid given. You want to go with a tetrahedron. Tetrahedron is an easy one here, though. Yeah, let's go with that easy one. That's another plain one, though. Oh, well. Two paraboloids? That's already here. The tetrahedron enclosed by coordinate planes. So coordinate planes are the x equals 0, y equals 0, z is equal to 0. So we might be in the first octant, probably in the first octant, and this plane. So we can imagine how this might look like in 3 dimensions. But let's first imagine how this would look like in 2 dimensions. So what this is asking us to do is the coordinate planes, and so one of the coordinate planes is the xy plane, right? And so xy plane, what can you say about a function and how it would look like if it was on the xy plane? What is the equation for the plane, the xy plane? Z is equal to 0. And so when z is equal to 0, you have 2x plus y is equal to 4. And that should just be a line that has a y-intercept at 4 and an x-intercept 2 or 8.
2 or 8.
Which one? 2. And since it's in the first, it's probably in the first octant. It doesn't say it's in the first octant, but the coordinate plane is when x is equal to 0, y is equal to 0, and z is equal to 0. So this is how it would look in the xy plane. So you can assume that the plane here, 2x plus y plus z is equal to 4, is above this. So that would give you your natural z limits, right? So that's it, without having to draw this out in 3 dimensions. As long as you can get yourself to draw in 2 dimensions, then you're all set. So our z is going to go from the xy plane, from 0 to this plane. And remember, when you're looking for these limits, you have to write your relationships between x, y's, and z's and all that, where whatever variable you have has to be by itself. So I would solve for z, and I would get 4 minus 2x minus y. So that's my 3rd dimension contribution. Now I'm back to 2 dimensions, and at this point I can integrate with respect to x or y first, depending on what you want to do. Since it's easy to solve for y here, I probably want to go with y first. So y goes from 0 to this line, where y is equal to 4 minus 2x. And then my x go from constants from 0 to 2. Okay? So that's my 2-dimensional region. And I got those limits from my two-dimensional region by looking at my two-dimensional picture. All right, let's set up this triple integral. We have a triple integral, and our integrand, we're finding the volume, so our integrand is 1. And we're integrating with respect to z first, and z goes from 0 to 4 minus 2x minus y. And then we decided we're going to integrate with respect to y from 0 to 4 minus 2x. And then with respect to x from 0 to 2. You have a question, or are you just squinting? Making me uneasy. Yeah.
Can we do a problem where z is not our first thing?
Yeah. But I can't hear you. Wait, before you say anything, let me do the inside integral first, right? Let's do the inside integral first. So the inside integral, the integral of this with respect to dz is just z, and then I evaluate this here, right? So it's 4 minus 2x minus y. So, whoops. Okay, so that's the inside integral. But now if I attach the other two integrals that I haven't done yet, 0 to 4 minus 2x with respect to y, and then 0 to 2 with respect to x. Jason, what were you going to say? So what Jason was trying to say was, instead of doing this using a triple integral, you could have used a regular double integral if you knew that the plane is on top and then the xy plane is on the bottom, and then you know the region. Then this is just a double integral setup. So we set this up like a triple integral, and then I integrated the inside once. But what we were saying is that instead of setting this up like a triple integral, we could have set this up as a double integral. And if we knew that the surface is this plane up on top, and then you want to find the volume below this surface, right? So the surface, we have a plane up on top, and then this is your region on the bottom on the xy plane. You would just do a double integral over this domain region over here of your surface, whatever your surface was. Essentially skipping this first integral step. So the surface is the plane. Z is equal to 4 minus 2x minus y. And then if I was integrating over this region, then this is your area. Yeah, it might not be so easy, yeah. Marie, did that answer your question? Okay. So, really, this is just looking at it as another application for the triple integral, but really you could do this with a double integral. Okay? All right, so one of the problems that you guys have in your homework is to write a specific integral 6 different ways. 6, right? It's dx, dy, dz, dx, dz, dy, dy, dx, dz, dy, dz, dx, and dz, dx, dy, dz, dy, dx. No, it's not. Your figure is going to be like that video. At least that's what I saw in your homework. It's going to be this thing. So let's do the one next to it. So it's to write the figure shown in the region of integration for the integrals looks like this. Rewrite the integral as an equivalent iterated integral in 5 other orders. So I mean, we'll do a couple, and then we'll say it's easy enough for you guys to figure out, and then you guys will figure it out.
Don't just start with the DZ.
Well, the thing that they gave you starts with a dy, so here's one way to write it already. So we can do dy and then dx dz. Should we do that first? All right. So there are 6 ways to write a triple integral if your region is nice enough to be able to accommodate for that. Because that very first example that we did, I probably wouldn't do this any other way other than the z first. So the z first is probably the best way and probably the only way, and then maybe I would do dx dy or dy dx. So I would write it 2 different ways, but I would definitely integrate with respect to z first here. Okay, because there's a big gap over here in the changing stuff. So I'll let you think about why that has a limited number of integrals, methods to integrate, versus this one, which you can integrate easily in 6 different ways. So let's see if we can get this set up. dy dx dz. So dy, if you're going to integrate with respect to y, I want to draw a line parallel to the y-axis and see where it enters and exits the region. And in fact, I know my y limits already. So if I'm going to do this with respect to y first, which is what they did, I'm just going to copy their limits for the y from 0. I put dy there. I just usually just put y, right? It goes from 0 to 1 minus x. And that's 1 minus x is this plane right here. Now they integrated with respect to z and then x, so this time we'll integrate with respect to x and then z just to change the order, which is our exercise here, is change the order. So what I need to do is I need to look at this shadow. So the first integral with respect to y is already taken care of here. Now I want to look at the shadow on the xz plane. And I drew it like this, where x is pointing to the right, right? And so I have to imagine how this is going to look like. Well, I know the function. Z is equal to 1 minus x squared. And so I think that's just a downward parabola moving up 1 unit. So this is that piece of the shadow on the xz plane. Now, if I want to integrate with respect to x first, I would draw a line parallel to the x and see when I enter my region and when I exit my region. So I enter my region when x is equal to 0, and I exit my region right here where x is equal to. I have to write this in terms of x. So that would be square root of 1 minus z. And usually when I take the square root of something, I need to compensate. Is it positive or negative? So in this case, they're both in the first quadrant where both variables are positive. So I just make a note there that it's positive. So that's my top limit. Right? And my z goes from where to where? Constants, 0 to 1. Okay? Okay, after I write it, slow down. So my f function, whatever that is, dy first from 0 to 1 minus x, the same y, dx next, and my x went from 0 to square root of 1 minus z, and then dz goes from 0 to 1. All right, that's one of them. 4 more to go. We're not going to do all 4 of them. You're not expecting all 4. We'll do one with the dx first, and then we'll do one with the dz first, and then there's 2 others within that mix. Good? Next page. So AJ wants to do x first. Let's do x first. Let me put my x limits over here. So I need to draw a line parallel to the x-axis. I don't know if you could see that. I can't turn this image. So x equals 0, and then I get out of this plane right here, right? I get out of this plane, and this plane is, I need x by itself. X is equal to what again? 1 minus y. That's it. So I have my x limits already. Oh, now that I have my x limits, I need to flatten this down on the yz plane. What is this image on the yz plane? It looks like a square here, right? Well, that's the rectangle. What happens when you have a rectangular region? What are your limits? Your limits are constants. So, with respect to x, first we go 0 to 1 minus y, and then if we decide we want to integrate with respect to y and then z, I just need to look at my yz plane and see what the limits look like. And in this case, they are constants, so I'm done with that. And then if I want to switch the order of z and y, because they're constants, I literally just switch the order of z and y. Then I would have the same limits for y, or for x. All right? What?
I feel like if you cut through the, or you're going through that top left part, it gets a different.
Right here?
Like near 0, 1. Or 0, 0. Is it not? No, you hit there. You hit part of the program. Yeah,
Where the arrow from equals 1 minus x.
yeah, right there.
Oh, bummer. Maybe it's not so easy.
Can you do it though? 2 different.
So I think if that's the case, then what we did is wrong. Wait. No, if it's wrong, it's wrong. No. Oops. That's not good. It's supposed to be a link that's downloadable. Did you guys try to download the graphing calculator files from before? No? Somebody asked me to put that up there and then they didn't download it. Who asked me? I forgot who. Oh. sucks. All right, let's see if we can recreate this surface. I have it done in another computer. Oh man, this is going to be a pain. That's not helpful. And we want to look at with respect to x first. Wait, this is the x-axis? Yeah. Whew. Well, the thing is that these things extend a little bit too far. All right, let me see if I could do this on the fly. So I'm going to make a parametrized surface with u's and v's. I think it'd be easiest to parameterize this triangle down in the bottom first. So I have a u and v. All right, that's one surface. Let's go to the next one. Next surface, let's parameterize it back. That one's easy. That's just y and z. So x is equal to 0, u and v. All right, two surfaces. Now, let's see if we can parameterize the top. So it's the same as the shadow on the triangle on the xy plane, except my z is going to be 1 minus x squared, but x is equal to u. See the top? And now we can cover it up with a plane. We got two more planes to go. Let's see, the first plane. Let's do the plane in the back. It's going to be u in the x. 1 plus u squared in the y, 0 in the z, or 0 in the y. And then I'll take this and add another parameter, v. There's that. And then the last one, oh, sorry. So the last one is, what is the last one? The last one is this plane. So we'll call x is equal to u. Y is dependent on that, and then v, this one goes up. So, if we look at it directly from the x-axis, so we're looking at the YZ, this is the picture that we get, which is a curve. There's a curve here, right? So it looks like with respect to x, if we're going to integrate this with respect to x, the lines that we're going through x should start with 0, but then they would change, like whoever, I think Jesus brought it up. So we're going to need to change that, and we need to figure out what this curve is, and then this is going to have to split up to two different integrals, two different triple integrals. All right, so let's scratch our work from earlier. Yeah, that's if you want to come up with x first, which is now telling me that we probably don't want to do that. If you had a choice, then you wouldn't want to do that. So should I erase this? Let's just keep it here and remember that it was a mistake. Okay, let's redo this with respect to x. So what's happening is that if you integrate this with respect to x, we have to look at what happens on the yz. And it looks like there's this place in the yz where it changes, our curve changes. I don't know if I can even tell what that is. But what we can do is to try to figure out what this is on the YZ plane. We're essentially looking at this intersection between the cylindrical parabola and this plane. Now, if we're going to find an intersection, we have to set a couple of things equal to each other, right? And it looks like they both have an x. Maybe we can just set the x's equal to each other. Let's get x by itself here. X is equal to 1 minus y. Let's get x by itself here. X is equal to square root of z minus 1, or 1 minus z. 1 minus z. And it's positive. I think we had this discussion earlier, right? This is positive. So if we set that equal to each other, we have 1 minus z with a square root is equal to 1 minus y. And now we have a relationship between y and z. I suppose we can square both sides. And then bring the z over, I don't know. So this looks like there is a shift. So your new vertex of the parabola is at 0, or 1, 0, or 1, 1. So that's right here. But in any case, this is the equation. This is the parabola right here. That means when we do our integral, this is only 1, right, out of the 6. When we do our integral, we're going to integrate with respect to x first. And when we integrate with respect to x, there's going to be two parts to this. One part is our integral with respect to x that goes through this plane. 0 to 1 minus y. And then we'll integrate with respect to, I don't know what, z first. So we draw a line parallel to the z. So this piece of plane over here corresponds with this part of the region. So if I integrate this with respect to z, I would draw a line parallel to the z-axis and go into 0 and get out when z is equal to whatever this is.
But if you look at the 3D picture, you still get coming out on top where z equals 1 minus x squared.
Not if I'm within this region. If I'm within this region, then I'm within this region over here.
If you go in from the bottom, you find it in the triangle.
No. So if I integrate with respect to x already, my three-dimensional picture is done, and I'm looking at my two-dimensional picture, and I'm right here. Okay? Well, we'll keep that thought and see if it changes as I go along with this. Your x, your z, and then your y limits go from where to where? Constants, 0 to 1. This z? Because I need to figure out what this is in the yz plane in 2 dimensions. And this z over here is where the cylinder and where the plane intersect. And so I found an intersection by solving both of them for x, and I set those x's equal to each other. And then I got a function or a relationship between y and z. So this is one way, or this is one part of this integral, but then we have another part of that integral that goes over here. And so now if we draw a line parallel to the x-axis, we would go from 0 to, I need to solve for x there. Oh, it's right here. Square root of 1 minus z. So now, if that's my x, I'm restricting my x area to just be this. And then I'll integrate that with respect to z first, and then y. So now if I integrate this with respect to z, I would draw a line parallel to the x-axis. I would enter my region at this function, 1 minus y squared. And then I would exit up here, z is equal to 1. And then my y goes from where to where? Now, this is just one answer where I integrate with respect to x and then z and then y, because these two things I have to add up as two different integrals. So my answer for this would be integral from 0 to 1, integral from 1 minus y squared to 1, and then my integral from 0 to square root of 1 minus z of the function with respect to x first, and then with respect to z, and then with respect to y, plus my other integral. So that integral, probably need to space this out a little bit more. So that integral goes to 0 to 1 minus y. And then it goes from 0 to 1 minus y squared. And then it goes from 0 to 1. So again, the order is dx, dz, dy. And we can't do this without having to do two integrals. So if you had a choice, you would not want to integrate with respect to x first. If you integrate with respect to y first, I think you can do that with just one integral. Because if you go with respect to y, you would enter through 0, and you would exit through this region, and then the other function over here would just be like a side of the cylinder. Well, that was a bummer. Okay, so there are times when it would be good to integrate with respect to one first versus the other, or in this case, there would be a time. This would be a time where we don't want to integrate with respect to x first. All right, so we just have to watch out for those things. All right, tomorrow we're going to try to finish up this section, and then the next two sections are. Do we have tomorrow? Yeah. And then we'll do cylindrical and spherical coordinates.